In section 7.5 and 7.6, we are going to work on right triangle trigonometry. So we are going to use those buttons on your calculator called sine, cosine, and tangent. And this is an area of right triangles. We will always be working with right triangles right now. And so we are going to write those sine, cosine, and tangent ratios in a right triangle. And we're also going to use those ratios to find missing side lengths in a right triangle. So if you create a triangle with a 90-degree angle and a 40-degree angle, and then you measure each side and write ratios, so you will actually discover that every right triangle with a 40-degree angle, when you measure the leg that's opposite that angle, so this would be the leg that is opposite that angle, and you divide it by the hypotenuse, and of course the hypotenuse is always directly across from the right angle, so that doesn't change. But if you measure the leg opposite and you divide it by the hypotenuse, that measurement will always be the exact same ratio. So if you created this triangle, and you could certainly do this and verify, but when you divide it and get a decimal for it, it's approximately 0.6. It's actually not exactly 0.6. It ends up to be 0.642787, etc. So really it's 0.642787, etc. But it turns out that because these are similar triangles, all of the triangles that you would draw would be similar, then because they all have three congruent angles, and the ratio of their sides would be the same proportion, and that is the proportional ratio, that 0.6. And it also holds true that if you measure the leg that's adjacent, so this leg right here is adjacent to the angle that we are referencing. So this is the adjacent angle. And if you take the adjacent length divided by the hypotenuse, you also get the same exact ratio. No matter who drew the triangle and how long the sides are, you will always get. Now, if we round to the nearest tenths, it's approximately 0.8, but it's actually 0.76604444, etc. And again, if you measure the leg opposite and you divide it by the leg that's adjacent, if you round, you end up with 0.8, but again, it's actually 0.8390996, etc. And the thing is, your calculator stores those ratios. So if you look on your calculator, you should have a sine, cosine, and tangent button. And this is the sine ratio, this is the cosine ratio, and this is the tangent ratio, and those are the buttons that are on your calculator. You should see sine, cosine, and tangent. Of course, they're abbreviated. So that is the basis of right triangle trig. Sine, cosine, and tangent ratios are ratio of lengths that help us find unknown angles and sides in right triangles. Again, this is only for right triangles. Now, we do have some other ways later on that we'll talk about if we don't have a right triangle. So to help us remember these ratios, we use an acronym called SOHCAHTOA. And SO is for our sine ratio, and that is the opposite divided by the hypotenuse. The cosine is our CA, and that's the adjacent divided by the hypotenuse, and the TOA is our tangent ratio. Now, I think it's sometimes easier to look at this as a fraction, so I kind of like this model. So we have so our sine is opposite over hypotenuse. Our CA is our adjacent over hypotenuse. So again, adjacent is for the A, hypotenuse for the H. And TOA, again, is our tangent ratio, opposite divided by adjacent. So when we look at this triangle here, if we use a right triangle, remember these always have to be right triangles. One of the most common or famous right triangles is a right triangle with side lengths of 3 and of 4 and a 5. We talked about that earlier. So if we look at A right here, if we're referencing angle A, if that's our reference angle, then our sine ratio of angle A, so our sine of angle A is the ratio of dividing the side opposite, which is 3, divided by the adjacent, by the hypotenuse, which is 5. That's our sine. Our cosine ratio for angle A is cos, so our adjacent side, which is 4, divided by our hypotenuse. And our tangent ratio for angle A is equal to the OA, so opposite side, which is 3, divided by the adjacent side, which is 4. So that's what we're talking about, those ratios. Now, if we're looking at a different angle, then the opposite and the adjacent sides will flip. If we looked at, for example, if we had a different angle marked B, now that would be different. The hypotenuse, though, however, will never change. So let's take our calculators out. Pause the video so you can take your calculator out. And we are going to, in just a minute, we are going to write those ratios or calculate those ratios. But before we do that, I want you to try to write the ratios for the sine of not angle A now, but of theta. So I'd like you to write the sine, cosine, and tangent ratios. So what would be the ratio for sine for opposite over hypotenuse? For cosine, ca, adjacent over hypotenuse, and tangent, toa, which is opposite over adjacent. So give that a try, get your calculator, and then restart. So if you did this correctly, these would be your ratios for this angle. Again, this is our opposite side, this is our hypotenuse, and this is our adjacent side to this angle that we're referencing. And so those should be your ratios. So let's continue. There is a slide here that we're going to get to where we are going to use our calculator. So let's practice this now, because your calculator stores those ratios. So we looked at, in our first example, we looked at the sine of a 40-degree angle right here. So if I scroll back here to the first example that we have here, we actually were doing the sine here of that 40-degree angle, and we took the side opposite over the hypotenuse, and we got this ratio. So now let's see what our calculator says. So I told you it was about 0.6. So take your calculator, and first of all, you have to make sure your calculator is in degree mode. So on your graphing calculator, right next to the second button, there's a mode button. So make sure when you hit mode, the third thing down, it says either radian or degree. Make sure you go over and highlight degree and then enter. And this will be the way for you to check right now. You need to make sure that your calculator is always in degree mode. If you do not have a graphing calculator, you need to find the mode piece on your scientific calculator as well, which could be in various places, but you should have that type of feature on your calculator. So when you type in the sine, so you hit the sine button, and then you type in 40, there'll be usually a parentheses. You can close it. You don't have to if you're just doing the actual ratio, but you get 0.6428. I'm going to round to 4 places because it's going to be more accurate. Actually, we're going to use the whole thing when we are calculating in general, but if you are going to get a decimal for it, you should probably go out to about 4 places. So if you go back to what we did, that matches what I wrote down, because every 40-degree angle in a right triangle, when you divide the side that's opposite by the hypotenuse, you'll always get that ratio. Again, the ratio of sides are proportional no matter how long our sides are, because our triangles are similar. So now you try the sine of 45. And again, if you get this correct, you should get 0.7071. Now we're going to try cosine. So if we do cosine, now that's the button COS, and the cosine of 37 gives us 0.7986. And tangent, now you have the tan, T-A-N button, try tangent of 62. That gives us 1.881. And the sine of 90 is actually 1. So your calculator has all those ratios stored for you, and that's how we're going to use it to find missing values. Okay, so backing up a bit, see if you can first practice writing and identifying the sine ratio of this theta angle. So again, what we're doing here is we are writing the or opposite side over the hypotenuse. See if you can write that. Then do cosine, which is ka. Write the adjacent side over the hypotenuse. And then T, tangent, is our TOA, right opposite over adjacent. So try those right now, and then check back to the notes later to see if you got them correct. So let's do one more together, where we are going to write the sine of angle B. So again, you have to know what your reference angle is. Angle B. Sine is opposite, so this is my side that's opposite over my hypotenuse. Well, I don't know my opposite side in this case, but remember, it's a right triangle. So I can get this side using the Pythagorean theorem. So I would take 9 squared plus x squared equals 100 squared, 10 squared, which is 100. Subtract 81 and you get x squared equals 19. So x is the square root of 19. I could get a decimal for that, but that's more accurate and more exact. So now when I write that, I'm going to write the side opposite, which is the square root of 19 over 10. My cosine ratio is the adjacent side. This is actually incorrect. Sorry about that. This is the adjacent side, and this is the hypotenuse. I wrote it correctly in my ratio, just not in my triangle. Since sometimes that is a helpful strategy, is just to identify. So now the cosine would be the adjacent side 9 over the hypotenuse, and the tangent, TOA, is, again, and I like to write these in there because then I can just look, oh, I want the opposite side for my angle, which is the square root of 19, and I want the adjacent side for my angle, which is 9. And so that's how we write those ratios. This is a little bit different problem. This is saying, hey, what angle are they referencing so that when you look at the sine of that angle, so what angle is this? That the side, again, so the side opposite of that angle is 6. And the hypotenuse would be 7.81. Well, this angle right here, the side opposite is 6. And if I do the Pythagorean theorem, that's going to give me 7.81. Or I can use a square root, leave it in simplest radical form. So the answer here is angle K is opposite over hypotenuse. So what angle would have tangent, which is TOA, the opposite side being 5? Well, here, this angle right here, the opposite side is 5. So, and the adjacent side is 6. So that would be angle B. And again, which angle would have the cosine, have the adjacent side 5? Which angle? Angle K or angle B has the adjacent side 5? Angle K does. So that's just working it in a little bit different idea, and again, making sure you understand that the side opposite or adjacent changes depending on what angle you're referencing. So now let's use these stored ratios in our calculator to actually set up a problem and solve for x using the idea of similar triangles. And the fact that in this case, every 51-degree angle There is a ratio that when you take this side, which happens to be the opposite, and this side right here, which happens to be the adjacent, so the ones that I need to deal with are O and A, which is our TOA. So for every 51-degree angle, when you take the tangent of 51 and you divide the side opposite by the adjacent, it's always going to be this exact same ratio. And you could actually get that ratio right now just to kind of show you how this works. If I type in tangent of 51, that is going to give me a ratio of 1.2349. Again, round to 4 decimal places for accuracy. So now what I really have is when I take the opposite side, which is x, and divide it by the adjacent 5, what I really have is 1.2349 is equal to x over 5. And if I put a 1 under this, I could just cross multiply, and I get 5 times 1.2349 is equal to x. So 1.2349 times 5 gives me x is equal to 6.1745 units. Now, when you give your final answer, here, you can round like to the nearest hundredth like we normally do. So this would be x is equal to 6.17 units. Okay? But the thing is, we've rounded that tangent of 51. So what's actually a better way, a more accurate way, is to just go back to this original ratio. Put a 1 under it. Cross multiply here. And take the tangent of 51 and multiply it by 5. And that is equal to 1x. So now on your calculator, give this a try. Type in 5, and then you can just hit tan. You don't even need times because it's going to multiply it. But otherwise you can hit times, and then 51. And that gives you that x is equal to 6.1745. So we basically get the same values. It's just that the second way, A is a little bit easier, and B oftentimes more accurate. So that's what we're going to be doing for the rest of basically this lesson. So let's try this one. I'll do another one with you. So now we are referencing this 45-degree angle right here. That's the angle we have. The sides that we have that are in relationship to that 45-degree angle is this 7 is an adjacent side, and that y is the hypotenuse. So that's an A and an H. So what trig ratio uses an A and an H? That's ca or cosine. So the cosine of that 45-degree angle will always be the exact same decimal ratio number when you divide the side that's adjacent, 7, by the hypotenuse y. And so again, I'm just going to put a 1 under this, and I'm going to cross multiply. So now I get y times the cosine of 45 equals 7. Now to solve this for y, I actually have to divide by the cosine of 45. So now y equals, and again, you can do all this on your calculator, 7 divided by the cosine of 45 gives you 9.899 units. Now, here's one of those times where one of those proportion properties that we learned, the means exchange. Remember, in a true proportion, I can switch the means or the extremes, and so now I could actually get to the proportion y over 1 equals 7 over cosine of 45, and notice that this was exactly what I did in my solving. So that's just a way to use one of those proportion properties, and that might be helpful for you and maybe a time saver. Okay, so I would like you to try this problem right here. I would like you to see if you can find the area of the triangle. The area is 1/2 the base times the height. So we need to find this value right here in order to do that. So that is our height of our triangle. So what ratio would you use? And how would you set it up? Go ahead and try that right now. So the reference angle 56, we are looking at trying to find the opposite side, and we know the adjacent. So opposite and adjacent is our TOA. So your setup should be tangent of 56 is equal to h over 40. This is the easy kind. When I cross multiply, all I have to do is multiply these two values together. So again, your work on your calculator would look like 40 times tangent of 56. And that should give you 59.3. So h is 59.3. So now I can find my area is equal to 1/2 the base, which is 40, times the height, which is 59.3, which gives you an area of 1,186 inches squared. All right. So one of the strategies, or one of the important pieces of using trig, is actually applications and word problems. So we're going to work on some word problems as we go through this. It says a pilot is preparing to land an airplane. He is on a straight line approach path that forms a 3-degree angle with the runway. What is the distance along this approach path to his touchdown point when the plane is 500 feet above the ground? So read it and then try to draw a picture. So if this is the runway right here, and here is the plane up here, okay, I'm not going to even attempt to draw what a plane looks like. Many of you are way better artists. But this path that he is on right here is making a 3-degree angle with the ground. We know that the plane right now is 500 feet above the ground, and we want to find the distance along this approach right there. So that's how you could draw a picture of that. Now, here's a much better picture, okay, if you take time and, I mean, this one obviously was done way better than mine, but the important part is not how great your picture is, but that you know what the triangle looks like. And so what we are trying to find here is that D distance. I called it X, they're calling it D. But what we have here is we are given the side opposite and the hypotenuse. So we have opposite and hypotenuse, so that's our So we're going to take the sine of 3 and set it equal to 500 over D. Again, here's where that means exchange comes in play. And so now I actually could say D is equal to 500 divided by the sine of 3. So now all I have to do, instead of cross multiplying, is take 500 divided by the sine of 3. And that gives you that the amount of feet he has left to travel, D, along that approach, is 9,553.66 feet. So that is our 7.5 and 7.6.